Morning to one and all. My name is C. Sohit, roll number 4J8, and I'm from ECE section. Today my topic is about analog integrated lock-in amplifier for optical sensors. Introduction. Our work that is described here advances a topology for an analog integrated lock-in amplifier, also called as LIA, for optical sensors. It is saying that we use analog integrated lock-in amplifiers in optical sensors, where we generally use them for in optical sensors, but there are some advancements which changes a topology in it. So it says that we developed a prototype for application in a plastic optical fiber sensor to measure the refractive index in an aqueous medium. This design aims at the integration of all system components in silicon and the generation of low power and low voltage circuit to allow its use in portable applications. The amplifier topology features differential inputs and outputs to mitigate problems with noise and interference. The prototype transimpedance amplifier occupies 0.374 millimeter square in a 0.18 micromillimeter CMOS process. Post-layout simulations indicate that the systems can operate with signals in a frequency range between 100 Hz and 2 kHz, which is able to reject the DC photocurrent component with a magnitude of up to 10 microamperes and can accurately process signals up to 14 microamperes of amplitude with a static power consumption of 275 microwatts from a unipolar 1.8 volts power supply. Optical sensors comprise a technology that has recently emerged in the wake of development and increased use of optical fibers and optoelectronic components in communications and consumer goods. Based on their operation principle or modulation and demodulation process, one can distinguish different types of sensors, such as those based on the measurement of the amount of change in luminous intensity, polarization, and phase and wavelength of the optical signal due to surrounding environment perturbations. A general characteristic of sensors in the relatively low amplitude of the generated signal. In some applications, the signal amplitude assumes the same order of magnitude or even lower than the noise generated by external sources and by the electronic circuit itself. Under these circumstances, the S or N ratio may display a value much lower than 1. So the use of traditional filtering techniques is impractical. In such situations, and when the sensor signal is amplitude and or phase modulated signal with known frequency, a lock-in amplifier LIA can be used to retrieve and amplify it, thereby improving the S-band ratio. What is system level operation principles and analysis? LIS, that is lock-in amplifiers, are based on the synchronous detection principle, which is used to highlight the input signal component that has the same frequency and phase as those of the reference signal and reject the other frequency components. This technique reduces the noise bandwidth and extracts a known frequency signal even if its amplitude is very small. The block diagram of a two-phase analog LIA is shown in the figure 1. Comprising an amplification path to two synchronous demodulators, each one consisting of the in-phase and quadrate channels and a reference signal path that generates an appropriate reference for the demodulators. A lock-in is said to be two-phase when it has two demodulators, one generating an in-phase component and the other a quadrate component. This scheme allows for the estimation of the amplitude and phase of the input signal without the need for adjusting the reference signal phase. A single phase lock-in, on the other hand, has only one demodulator and therefore requires a phase adjustment circuit to recover only the amplitude of the input signal. So this is the block diagram of an analog two-phase LIA. LIA is called two-phase when it is said to be having two demodulators, one in generating in phase component and the other a quadrate component. So we can say that this is the modulated signal and this is the amplification path, in phase path, quadrant path, and different signal path. This result highlights a method used to synchronize the demodulator input waveforms, which is termed the null shift procedure, considering a single phase LIA and starting from an arbitrary initial phase condition. The reference phase is adjusted so that the demodulator presents a zero value at its output. This condition indicates that the demodulator inputs are in quadrature, therefore, by shifting the input reference phase by 90 degrees, the desired in-phase condition given by is obtained. This procedure can be carried out even under noisy conditions, maximizes the output DC response for symmetric periodic signals, and nearly maximizes the response for asymmetric periodic signals. Of course, when considering two-phase LIS, a null shift procedure is not necessary, as the output of the in-phase and quadrature parts correspond to the component of a phasor. Now, the proposed lock-in amplifier architecture will be like the LIA architecture proposed in this presentation is presented in the figure 2 in the next slide, where it can be observed that all building blocks have a fully differential topology to mitigate the noise coupling problem, to improve supply, noise immunity, and dynamic range, and consequently by the SNR. Moreover, phase adjustment circuitry to allow the synchronization of the mixer input signal is avoided. An externally generated reference signal is applied to the local oscillator, part of the mixer through a function or arbitrary waveform generator. So this is the proposed lock-in amplifier architecture, where this is built mainly to reduce the noise effect in this signal demodulation, and moreover the phase adjustment will allow the synchronization of the mixer input signals. We generally take the reference signal from this from the outside of the circuit for differencing with the input signal, and this is the total architecture of the LIA, where one is that quadrature behavior and one is for in-phase behavior. And coming to the conclusion, the architecture of an analog single phase lock-in amplifier implemented in a 0.18 micrometer CMOS process was advanced, and its feasibility was demonstrated by means of post-layout simulations and comparisons. With theoretical predictions, the proposed architecture presents interesting features not commonly seen in other designs, such as a fully differential system and constituent blocks, including the unconventional differential sensing of the unbiased photodiode. It also carried out the integration of the large time constant output low-pass filter, which requires a cutoff frequency that tends towards DC and a steep characteristic. Thank you.